Hello, everyone. Welcome to another GOAT seminar. Today we have Manolis Vasilakis with us, and he will present us his work about bounded degree vertex deletion.
So, hi, I'm Manolis, and this is a part of the work that I had with my supervisor, and we are both at Paris Dauphine in Paris. So, I will talk about pretty much half of what we did in this paper, but it's pretty much the same techniques could be applied to other problems as well. So this is what we did. We had common techniques applied to two different problems. And this is a brief outline and maybe a bit of motivation at the start. So in a lot of cases, we have some NP-hard problem, which is sad or good if you are a cryptographer, I guess. And the good thing is that, okay, in some cases, it might be easy in some graphs, let's say, if it is a graph problem. So the idea would be for parameterized complexity would be, okay, what happens if the input is pretty much close to being nice, in the sense that the problem is easy. And this is the motivation behind this area. So here we just try, hopefully, to confine the exponentiality to the parameter, to the distance to the parameter, actually. And, okay, so what becomes important is actually the structure and not the size. And it's not that this becomes important, it's in fact that this is important. This is the important part. It's just that we did not know it before, I guess. And yes, the idea is that as the parameter increases, we have an exponential increase to the running time with respect to the distance to the parameter. So this is, and because every graph is at some distance from a tractable case, the exponentiality comes from this distance exactly. And we will say that the algorithm is FPT for a given parameter when we have such a running time. And if we do not have such a running time, then our problem will be said to be W1 hard. So it's not that we do not have such a running time, it's that we believe that we do not have such a running time. So yes, this is a bit, and I will also go very quickly, I guess, over some structural parameters that we will use. So here we define the path decomposition, and I have stolen this picture from Wikipedia. And the idea is that, okay, we're given a graph, and we want to somehow embed this graph in a path, and just considering in our new graph slightly fatter vertices. Each one contains a subset. And the important property is that actually, if we look at the positions in the nodes of the path decomposition that contain a given vertex of our initial graph, then this is actually a subpath. So those nodes are connected. So this is the idea. And the width of a path decomposition is the minimum size of a node that we have. So it's actually, we try to minimize the size of the sets that we use. And okay, then tree width is defined analogously, but for trees. So the decomposition now is a tree, not a path. And okay, vertex cover is of a graph is the minimum, the size of a minimum deletion set to an independent set. And tree depth for a graph is defined like that. So the idea is that, okay, we look at if our graph is not connected, then the tree depth of our graph is the maximum over the tree depth of the connected components. And the interesting case is the middle one, where we remove one vertex and we hope for the best. So we minimize over the tree depth of the remaining graph. So this actually has another definition via something called the elimination forest, but yeah. So those are quite usual parameters, and we have a lot of results parameterized by those in structural parameterized complexity. And these are some of the most used, I would say. Okay, and some about the relationship of those parameters that we define here. So those are the parameters that we will look at. Actually, we will not even look at tree width, in fact. It's just that the lower bounds are for path width, and it's just that the upper bounds, the algorithms work for tree width as well, as it is quite usual. So we have this inequality there that everything is nicely placed in some way. And the interesting thing and the main motivation is that, okay, if you consider a set of graphs that have vertex cover at most C for some constant, and the set of graphs that have tree depth at most C for the same constant, then the first is a subset of the latter, right? Because we have this inequality for every graph G. So the interesting thing is that, okay, if I give you an algorithm for the bigger of those two sets, then it will obviously work for the smaller as well. And if I give you a lower bound for the smaller of those two sets, then it will also work for the bigger of the two sets as well, right? Right. Okay. And okay, we have this weird thing with the arrows denote. The arrows in general do not denote this linearity in this inequality, but okay, it's fine. Okay. So the main question that we ask ourselves is this type of price of generality questions. Like we look at a set of graphs, the set of bounded tree depth, or a set of bounded tree width, and so on. And we ask ourselves, okay, what's the best algorithm that we can have that's applicable to this set? And we have this kind of one set of graphs, a subset of the other, according to the previous figure. So this does not always, we have some transition in the running time. And our goal is actually to find the optimal runtime for each such parameterization. So this is what we aim to do. And to do that, we have to, find an algorithm and then prove that it is optimal, that we cannot do better. So in this talk, we will actually only go to the latter part. So we will only talk about lower bounds. And we will try to prove that, okay, the known algorithms are actually optimal. And to do that, we will use some tools from fine-grained complexity. And by some tools, I actually mean the ETH and the strong ETH, which I will define. So I guess we all know K sub as a problem, and here is a formula, and K is the number of literals that we have at most that many per clause. And here are our hypotheses. And the first one tells us that, okay, you cannot solve 3 SAT in time 2 to the little o of n. And the latter actually tells us that, okay, for every epsilon, there exists a K SAT for some K such that you cannot go under 2 minus epsilon to the n. And the thing is that we have this kind of implications. So strong ETH implies ETH, which implies P versus NP. And those two hypotheses are very commonly used to show lower bounds in parameterized complexity. And I think that this is the end of the preliminaries. And here's the problem that we will work on. So this is a generalization of vertex cover. And essentially, we want to delete at most k vertices such that the remaining graph has degree at most delta for a given k and delta. So for delta equals 0, this is vertex cover, right? And yeah, for instance, in this graph, if I give you a budget of 1 and I ask you to delete 1 vertex so that the maximum degree becomes 2, then you can actually delete whichever vertex you want, right? So this is a yes instance. If I ask you to delete at most one vertex and delta equals 1, then this would have been a no instance. So yes. So I guess the problem is quite clear. And so what we know about this problem is a lot, but the most relevant is that it is W1 hard by tree width. It becomes FPT by tree width plus K. K is the budget that we have, the size of the deletion set. And then there was this paper, this is a full version. I think that the conference version was from 2018 or something, where they proved that the problem is W1 hard parameterized by distance to trees of height 3 or something like that. So I am actually cheating a bit. Like, they did not just prove that the problem is W1 hard by tree depth, but the result was stronger. But as a corollary, they obtained that, okay, in the end, after a series of reductions, they actually show that we cannot solve the problem in that running time under the ETH. So we have such a lower bound coming from this paper. And then there is this general subset convolution technique that can be used to obtain a DP algorithm of running time delta plus 2 to the tree width. And in the end, you can also obtain a vertex cover to the big O vertex cover algorithm, which again, you use a win-win argument. So in one case, you actually reduce to the DP algorithm, and in the other, you do some reductions to some domination problem, and again, you get the same running time. So the thing is that, yeah, if you think about it, also this algorithm gives us this algorithm, right? Because delta is at most n, and tree width is at most treated. So yeah, so the thing is that all of those algorithms are doing DP, right? Which is interesting. And what we show is that, okay, you can actually not do better in any of those cases. So under the strong ETH, the DP algorithm parameterized by delta plus tree width is tight. And then we have two lower bounds under the ETH, one for the parameterization by tree depth and the other by for the parameterization by vertex cover. And so yes, everything is tight, which is good. But the most interesting thing is that actually, yeah, there is actually dynamic programming hidden in all of those. And apparently this is the best that you can hope for some weird reason, but yes. So I will talk about the first of the results now. So for the first of the results, we have that, okay, it's the lower bound parameterized by delta plus tree width. We will reduce from this CSP problem, which is quite helpful if you want to show a lower bound parameterized by tree width where the base of the exponent is not 2. So this allows us to simplify the constructions. So this is in some sense, no, this is a CSP problem. And every variable can take among B values. And you're given like the clauses, the constraints, involve at most Q variables. And you have at most, B to the Q satisfying assignments for every constraint. So for instance, we have this example here, and like a good assignment that satisfies both constraints would be x1 5, x2 2, and x3 2, right? So I don't know if we have another good one. Probably not. Yeah. So there is this theorem by Michael that allows us to kind of simplify a lot the reduction. And in a sense, it's very useful for the base of the exponent. Like instead of starting from a SAT instance and then doing some doing some gadget so that you encode a group of variables of some specific size to this other thing, you can pretty much go more straightforward here. And this simplifies a lot the constructions. And this tells you that, okay, for any B, if you had such an algorithm for any constant Q, then SETH fails. So this is the starting point of our reduction. And actually, our reduction, okay, so this is what we will show. And our reduction is actually pretty much a group of reductions. So essentially, it's a different construction for every different delta. And now I'm cheating a bit because actually it's two cases. One generalizes nicely, and the other is just when delta is equal to 1, which needs some specific handling. But essentially, it's a family of reductions. And the way it works is that, okay, we fix a Q, which is a constant, right, from our theorem, and an epsilon, and we start from such an instance, constraint satisfaction instance, and we want to produce an equivalent instance of our problem for delta being equal to b minus 2. And the path width of our graph should be not just linear, but actually n plus a constant. So this is what we aim for, and this is what we do. So in that case, if we had such an algorithm for the bounded degree vertex deletion problem, this would result to a b minus epsilon algorithm for every Q for the constraint satisfaction problem, which in turn results in SETH failure. So this is the thought process. And what's the high level idea? Well, we will have, now we follow a lot these the constructions of this paper by Lokstanov. That, okay, you actually, where they proved that a lot of problems are typed, under Lewis. So the idea is that we will have a block gadget which encodes an assignment for a variable. So for all of our variables actually. So in that case, for a variable, in that case, this should have like delta plus 2 logical choices, because this is the number of values that a variable can take. So delta plus 2 is equal to beta, to b. So yeah, we intend for our problem to have pretty much delta plus 2 logical choices, or if you want, like locally optimal solutions somehow. And then we will construct n parallel block gadgets, one per variable. And we kind of extend this construction and serially connect it, because every block gadget is used, every column of this construction will be used to verify that one constraint is satisfied. So we want to verify that all of the constraints are satisfied. So we pretty much repeat this construction once per constraint. Yeah, so we have for every column a constraint gadget that pretty much checks out that, okay, we satisfy this constraint. And the path width of the graph is, on a high level, it's n parallel paths plus some constraint gadgets, but those are of constant size. So the total path width of the graph is actually n plus a constant. And for the case that delta equals 1, this is what it looks like. So if you think about it, for every 3 consecutive vertices, if we want our graph to have maximum degree 1, we have to delete at least one of these 3 vertices. So the deletion actually encodes the assignment of this variable. And then this C is this constraint gadget, which if your deletion works out, then from the gadget C, we do not really have to delete a lot of vertices. I mean, the difference is always +1 actually. So we always have to delete a lot, but constant a lot. And in the bad case, we have to delete constant a lot +1. So things do not work out. And for instance, here, we pretty much have that, okay, in the first constraint, we have that the pair x1 equals 1 and xn equals 2 satisfies it, right? So this is where the addition comes from, where the edges kind of come from. So those are not exactly edges, but whatever. Okay. Yeah, I hope that it's clear the general idea of how this kind of works. So the thing is that the picture is quite nice for delta equals 1, but for larger delta, it becomes uglier. So this again, a block gadget. So this is used to encode delta +2 choices for a single variable. And the idea, and then here is how we serially connect those block gadgets. And the idea is that, okay, for the delta +1 choices, we delete B and we choose a number of vertices to delete from the xi's and then the rest of them from the yi's. And this results in A prime having a couple of vertices from its left side. You know, so A prime is actually this vertex in the middle, right? It's A prime for one gadget and A for the immediate afterwards gadget. So on a high level, when I delete some vertices from the yi's from the left gadget, I actually enforce a remaining budget that forces me to delete some of the vertices from the right gadget, because remember that our degree in the resulting graph should be at most delta. So this kind of allows us to enforce that if we cheat on the assignment, because we have to somehow enforce that in the two gadgets we make the same deletions. If we cheat one way. And in one way, I mean that we will not, we cheat in a monotone way. So we can actually bound the number of cheats that we make. So yeah, this is the main idea. This is why we need this complicated thing. And the extra assignment comes from deleting vertices A and A prime and some other stuff, but we do not really care. So again, this captures like delta +2 logical choices. And yeah, afterwards we pretty much, you know, do the same thing, right? We have this block gadget here connected with the immediate next block gadget there and so on. And again, we have this constraint satisfaction gadgets. So that's it for this. I hope that it's kind of clear. Okay. I mean, there is not a lot of novelty in the sense, like we not use a new technique. It's just about finding the correct gadget. And now about the now about the tree depth lower bound. So we have an algorithm for delta plus tree width, which actually implies this algorithm. And the question is again, okay, can we do better if we look at only the graphs of that much tree depth? And we prove that no, we actually prove that this algorithm is the best that we get, even if we look only at graphs of bounded tree depth and not all of the graphs of bounded tree width. And the high level idea is again, as usual, we reduce from the K multicolor click problem. And we know that under ETH, this does not have such an algorithm. And we will construct an instance on a graph H and some budget K prime and a degree delta of our problem, such that the two instances are equivalent. And we also want to keep the tree depth of our new graph actually linear in K. And the reason for that is that, okay, if the tree depth of our graph is some function of K, okay, this suffices to show W1 hardness. But if we want to look in more fine-grained questions, this actually implies such a lower bound. but we want to be like really tight. So we want to prove that, this was, we want the linear function.
Very small.
Yes, this would be small. Yes. Okay. So I will start with a sketch, and then I will throw an ugly picture, some ugly picture. But yes. Okay, so we start from an instance of k multicolor click, and we further assume that k is a power of 2. So if it's not, we just add some independent sets and connect it with everything else. And we have a choice gadget for every independent set. So the independent sets will be the VIs, right? In our k multicolor click. And we start for every such independent set, we have a choice gadget, CI, which actually encodes a choice of the vertex that is in the click. And then we actually show how we can make copies of this gadget that are consistent in the sense that they encode the same choice, but with only using a constant number of additional vertices that connect the two choice gadgets. And then we have this adjacency gadget, which has like 4 numbers as input. And the idea is that we want to check whether every independent set indexed I is connected with, like, the choice in the independent set VI is connected with the choice in the independent set VI prime, where I and I prime run through these values. Okay, so this is what we try to show. And the construction for that is, okay, we have the choice gadgets. And the idea is that we create, for a specific adjacency gadget, we build it recursively. So it is constructed by 4 adjacency gadgets, which are defined due to the upper and lower halves of I1, I2, and I prime 1, I prime 2. And then we just pretty much enforce consistency between the different occurrences of the same choice gadget. And okay, the idea is that if we delete all the copy vertices from this thing, we end up with all of the adjacency gadgets being disconnected. And in the end, the function for tree depth is something like that. And yeah, this is a really nice picture. I hope that everything is super clear now. So the idea is that, okay, I give you, on the left side, we have the choice gadgets for VI, for every I from I1 up to I2. And on the top, we have the choice gadgets for VI prime, for the I prime running from I prime 1 up to I prime 2. And if we want to check that we have an edge from every choice on the left to every choice to the top, we just do it recursively. So for every choice gadget, we produce 2 copies. We enforce consistency, and this is what those dotted, not dotted, but okay, those lines represent, that we kind of enforce consistency. So for every connection between different occurrences of the same choice gadget, you can think of it as a constant number of vertices that are connected in a way that enforce that the choices remain the same. So yeah, if we delete all the copy vertices, so if we cut all of those edges, what remains is actually disconnected, right? We have 4 occurrences of an adjacency gadget, in which case it is actually much smaller, right? Because I and I prime run for half of the set, right? So I hope that the high level idea is clear. So this is what we do pretty much. And then, okay, this is how a choice gadget looks like. So we have like some vertices, and the idea is that, okay, we will delete the optimal deletion will delete with at most with exactly n different ways. So the different ways will be, okay, how many vertices from the top independent set have I deleted and how many from the bottom independent set have I deleted? And this is how a copy gadget looks like. So we have two choice gadgets and we add two vertices and we connect them this way. And if the choices are consistent between the two occurrences of the choice gadget, then actually the degree of G1 and G2 is delta. Otherwise, at least one of them has degree over delta. So in an optimal solution, we have to delete something extra. So this is the idea. And yeah, this is an edge gadget. This is how it looks. We create something like that for every edge. And in the adjacency gadget, for the base case, where we want to check the adjacency of just two independent sets of the choices in two independent sets, we have a construction which looks like that, where you have something like the two choice gadgets, and then four vertices that, okay, they have some leaves attached, but whatever. And then for those four vertices, we have edges towards all the relevant edge gadgets. So again, from the base case for the adjacency gadget, for the base case, we have to delete just four vertices, and then we disconnect a lot our graph. So the tree depth becomes constant for this case. Yeah, I don't know if things are clear, kind of. But yeah, so this is a technique that actually we believe that can be used elsewhere as well. I mean, we did use it in another problem as well, and we believe that it can be used to a lot more. Okay, and finally, I will talk about the vertex cover lower bound. Here I will get into slightly less details. But yes, so this is the result that, okay, this algorithm is tight under ETH. And here we will start from this problem, which is a variant of SAT. So it's actually a variant of 1 in 3 SAT. So we don't want to have a satisfying assignment. We want every clause to have exactly one true literal. And also every clause contains exactly 3 variables, and every variable appears in at most 4 clauses. So this is a variation of one in 3 SAT that actually we know that under the exponential time hypothesis, it does not have such an algorithm to the little of n. And the idea is that we will start from such an instance, and we will construct an equivalent one of bounded degree vertex deletion, where for the vertex cover of our graph, it will be actually n over log n. And why is that? Well, the reason is that if that is the case, then if we had such a running time for our problem, we would get 2 to the n over log n times log n minus some stuff, but smaller stuff. So this would give us a 2 to the little log of n algorithm for this SAT variant, which cannot be the case under ETH. Okay, so I hope that's clear where we start from. And now we'll talk about what tool we use, which again, we think that it will be useful for other problems as well. So there is this thing called the d-detecting family, and we're given a set U as well as 2 functions from U to 0 up to d minus 1. And assume that for a subset of that, of our universe, f of a is defined as the sum of the values of every element that it has. And the 2 functions are equivalent if actually they map every element to the same value. Okay. And we say that a query is, when we make a query, we say that we check whether f of a is equal to g of a for some a subset of our universe. And okay, if you think about it, this we can check whether 2 functions are equivalent by making as many queries as is the size of the universe, right? Because for every element, we check whether f of our element is equal to g of our element. And if they differ in at least one, then they are not the same function, right? And the question is, can we do better when we consider also subsets, or not just singletons, but subsets of our universe? And the answer is, so this is essentially what we ask, whether we can check this. And the answer is that, okay, and actually, if we have a set of subsets such that for any two functions, if they are different, there is a subset contained in F that verifies that they are different. This is a detecting family. Yes. 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 And there is this theorem that for every constant d and finite set u, one can compute such a detecting family in time linear to the size of your universe. And actually, the size of the detecting family is u over log u. So it's not linear, it's less. Okay. So this is what we will kind of use. And the main idea behind is the following. And this is why we start from this 1 to 3, 1 in 3 sat thing. So our elements in the universe will be the clauses. And our detecting family will run from 0 up to 3. And we will actually count the number of literals that are true. So this is the intuition behind. Okay. So we will kind of construct, our graph based on the detecting family that it is less than linear in the size of the clauses. And this will allow us to actually delete all of those vertices and having a vertex cover which is less than L on a high level. And I will talk a bit about the construction, but we will start from an instance phi. And we will partition our variables and our clauses into groups of this size and that many. And actually, the reason when I write appropriately, I mean that for every closed group that we have, for every CI, it will actually have at most one clause that contains a variable from Vj. And also, if a variable from Vj appears in a clause, in a closed subset, then it will appear only once. So this means that we have some kind of one-to-one correspondence in the sense that when we talk about a variable subset Vi and a closed subset Cj, then there is at most one variable from Vi that is contained in the whole of Cj, and actually this variable is contained in exactly one clause of it. So this is the trick behind this, and we can do this partition in polynomial types. So again, the idea would be like we have a choice gadget graph for every variable subset, which will encode the assignment of those variables. So pretty much this graph is actually of size n, because the set of variables that Vi has is of size log n, so we will have one vertex per assignment. And then for every closed subset, we introduce that many vertices. And actually, these vertices are actually obtained by a d-detecting family on the function where d is equal to 4, because your function goes from 0, because you might not be satisfied, up to 3, because it might be that you are satisfied due to all of your literals. And pretty much these vertices are obtained by a detecting family of the clauses of CI. Yeah. And for the vertex cover bound, we just delete everything produced by the CIs, which is, okay, we have square root of n closed subsets. And for every closed subset, we have a d-detecting family of size square root of n over log n. And so if we delete everything from there, we end up with a vertex cover of size n over log n. And that's it. So in conclusion, we have shown that some parameterized algorithms for this problem are optimal under those hypotheses. And actually, the best that we can do in all of those cases, actually what is hidden behind is dynamic programming in all of those. And yeah, we don't know whether we have this bound as well for feedback vertex set. So the reduction they mentioned in the beginning, where they showed the W1 hardness by tree depth, it was a deletion set to trees of height 3. So they do obtain a quartic lower bound as well, but we don't know whether we can do better for graphs of bounded feedback vertex set. And that's it. And thank you.
I was wondering whether you could use similar techniques for deletion to degenerate graphs. They're like you don't bound the maximum degree, but like the minimum degree in every subgraph. So the most prominent example problem from this set is feedback vertex set. This way.
You want bound the minimum degree?
Well, like you delete some vertices so that the rest of the graph is degenerate.
Yeah. I don't know. I don't know. I don't know.
I was going to ask a similar question because Manolis, you said that you studied two problems at some point.
Yes.
Which one was the other one? And,
so the other one,
it's
again something to do with maximum degree, actually. So it's a problem called defective coloring, where you aim for a coloring such that every vertex has at most delta same colored neighbors. So it's again you play around with the degree pretty much. So this is a trick, and you play around, you enforce your constraints because you bound the maximum degree. So if you want to bound the minimum degree,
I mean, this is a lot to do with coloring. If it's degenerate, then you can definitely color it with D plus 1 colors.
Yeah, I don't know. It might work. Yes.
So I think that the more general question from what they proposed was, what other type of problems could you see these techniques being applied to?
Well, actually, I believe that the trade-off one is very general. I mean, we applied it to maximum node disjoint paths, and it pretty much works. Like the only thing that you have to do is have like a choice gadget, and then prove that okay, you can create a consistent copy of that with a constant number of vertices, and things work. So I believe that actually this will work in a lot of problems. So this, I don't know. For the vertex cover one, I don't know. I mean, we really play around with the degree. I mean, that's true. Yeah, I don't know.
I actually have one more question. Because in your reduction, you're reducing from multicolored tree, but you're not using the standard thing where people are checking the adjacency between the sets in such a way that you then get a square root lower bound. So one thing that people usually use is a reduction from partition subgraph isomorphism, but there you get the lower bound is less, like the exponent is less.
Yeah, and over log n. Right?
So I was wondering whether your technique is like a bypass to that and then could be used more generally or
Yeah, I don't know.
Food for thought.
Maybe because as long as you pretty much as long as you prove that okay, I have the consistency for free. Okay, you only pay constant. Then yeah, this allows you. Yeah, maybe.
But you're gonna need a gadget that forces an edge and a gadget that forces not have an edge. Both of them should be cost aside. But yeah,
No,
if you can
I haven't
manage
thought.
that. Do we have other questions? If not, let's thanks the speaker again.